Hey, it's Nicole here from Shared Everything, and I have two world experts on digital twins and digital twin infrastructure. I have Wes Brewer from Oak Ridge National Lab and Adrian Jackson from EPCC. Wes, let's start with you. What are you working on in this area?
Yeah, hi, Nicole. I've been working for the past 2.5 years on developing a digital twin framework for liquid-cooled supercomputers. And so we're modeling the power and the cooling and the workloads and what's going on the system itself.
Okay, we'll come back to that in a minute because there's interesting stuff in there. How about you, Adrian?
Yeah, so like Wes, I've been working a little bit alongside him on the same digital twin. So working on looking at modeling our data center infrastructure, and then how it interfaces with the supercomputers that we run and people's actual applications running on those supercomputers. But I've also spent a bit of time working with aerospace manufacturers on digital twins of jet engines in that sort of engineering use case. And in the past, a lot of the work I did was with fusion scientists on individual components which could be put together to working with digital twins. And I've got colleagues who work quite a lot with weather forecasting organizations as well. And you could sort of see a lot of what they do as a form of digital twin as well, I think.
Okay, well, I love this already because we have a practical standpoint in terms of power consumption and how all of this is going to work as we scale in the future, and also some real world use cases. Wes, I'm going to start with you. Just for people that are maybe a little bit new to this, what distinguishes digital twins from what we've always known as like HPC simulations from days of old?
That's a good question. And I think when I hear people talking about digital twins, I think there's a general confusion about what is a digital twin. And sometimes it's conflated with just a traditional simulation. So there's been several different groups that have identified about 5, sometimes 6 different levels of digital twins. And so what I like to think about digital twins is it's not just a simulation, but a simulation is part of a digital twin typically. So some of these different aspects are, one is major part is actually bringing in system telemetry data from the physical system and integrating that into the simulation itself. You also typically have machine learned or AI models that are modeling parts of the digital twin, and then you typically have a feedback link that's feeding back to from the digital twin back to the physical twin for doing autonomous control and things like that. So there's generally, I mentioned, 5 different levels, and the first level, the simplest digital twin, is sort of like just modeling the assets. So this is like 3D asset modeling using like Autodesk or SolidWorks, something like that. And then the level 2 would be sort of bringing in the data, the telemetry data from the physical system into the digital twin. So maybe visualizing your 3D asset model with your telemetry data. The third level would be using that telemetry data to train a data-driven model. So training like a machine learned model from your telemetry data that's predictive. And then the fourth level would be your traditional simulations. And then the fifth level would be actually developing an autonomous control agent that can feed back to your physical twin. And that's generally done using reinforcement learning.
That is a lot of moving parts. And
Yes.
I remember back in the days, when people first started talking about digital twins, I don't know what year at supercomputing it was kind of a new thing. When was that, guys? Like 2015, maybe 2016? I'm not sure I remember. Maybe it was earlier than that. But at that time, it just kind of felt like an extension of traditional modeling and simulation, but on a larger scale. But now, as you said, we have AI, we have far more devices operating at the edge that can feed in real-time information. So what you're saying, Wes, is that these digital twins require a real-time component, maybe an AI agent argumentative component where they're talking back and forth, plus traditional simulation data. So that's fascinating. Before we move on to Adrian, just so we stay on this point, what does this mean for power? I mean, this is your area. How power hungry is this compared to what we're looking at with AI, for instance?
Well, I mean, when you talk about power, we actually developed a digital twin, and one of the main purposes of our research was to look at a study energy efficiency of supercomputing. And so, with people, the different groups continuing to want to build larger and larger AI, more complex AI LLMs like ChatGPT, these are requiring larger and larger supercomputers, which is driving up the power. And so we wanted to actually have a way to be able to study energy efficiency. And so we developed a digital twin to do that. We work with the Frontier supercomputer. So the power, that was the first exascale supercomputer. Peak power consumption is about 28 megawatts. So generally the system's going anywhere from idle state of 7 megawatts up to 28 megawatts. And so I don't know if that answers your question, but that's what we're dealing with.
It answers my question and raises about 55 others, but we'll have to get to some of those at another time. Adrian, so you explained what you were working on, and it sounds like there's a real world component there. So how is some of what you're doing building on what Wes just explained in terms of this very complicated moving parts kind of workflow?
Yeah, so I think I have a slightly more permissive sort of view of what a digital twin is, but very much it's these sort of multi-physics simulations, it's these simulations and incorporation of operational data and external data into one system that tries to really model something that's happening in real life. We have, just as Wes has said, there's these 5 different stages. There is a whole different spectrum of digital twins, from things that you can nowadays model in real time to things that are still far too complicated and expensive to model in real time. You can see that really with something like weather forecasting. You could consider a weather forecast nowadays very much to be a digital twin because components have been added to traditional simulation over time, which include, more atmospheric chemistry, more environmental chemistry, more data sources. We've got satellite data, you have more deployed things, and then people are starting to bring in machine learning approaches as well, so generative AI to fill in areas where we don't have enough sensor data and those kind of things, and trying to couple them all together into something which really is as close to what you can model as the real world. And of course, the thing with weather forecasting is you're not trying to do necessarily real-time operation, you're trying to project into the future. You're trying to say what happens if we do this, what's going to happen in the next few days, can I plant my crops because in 2 weeks time it's going to be frosty or it's not going to be frosty. And so there are some digital twins like the one that Wes and myself work on, where you may be looking at modeling real time what's happening to your data center and your system, and can we optimize things there. But they also have these use cases where you can say, well, actually, can we predict what would happen if we changed how our system was? Can we change things like how hot our water is in our cooling loops, or what level of electricity we provide to the racks? And then use that to optimize how we run these systems and how we build these systems and how we operate these things overall. I think that goes across all these places that are trying to use digital twins. It's giving you something to predict what's going on now, and giving you a tool to explore what you can do in the future. Now, you asked about, does that make it expensive? Does that make it power hungry? How does it compare to AI? And of course, there's no real good authoritative answer to that. But what you can see is that parts of these simulations and digital twins and approaches can be approximated with machine learning approaches. And here we're talking about machine learning inference, so a model that's been trained and then used as part of a digital twin. And that should reduce the computational costs and the power required over time. Obviously, training the networks is expensive, but once you've got a trained network, it should be quicker than a comparable simulation approach to that. And that's why we want to include them inside the digital twins, to actually try and make that twin less expensive, although the initial training part of it may be costly in the first place. I don't know if that helps at all.
It does. Again, you guys keep talking about things that just make me want to ask question after question, but I'm gonna stick to the script a little bit here. What are the infrastructure challenges beyond power that we talked about? So I know, Wes, you're working on the Frontier supercomputer. Adrian, you have a number of resources available to you there at EPCC. So if we want to make these things practical in the real world, and we want HPC, by the way, to pave that, what do you need still? Where are the bottlenecks? Where doesn't this work at a certain scale? Because scale is everything, right?
So I think for us, one of the challenges for us is that to model like an exascale supercomputer with all its complexities, there were some trade-offs we had to make in terms of the level of fidelity. And so, for example, if you want to model every single instruction on a GPU, you can do that, but you can't take that simulation and scale it up across 10,000 or 40,000 GPUs that we have. It just becomes computationally intractable. And so for us, we had to find a good balance between the types of tools we were using, sort of approximations and fidelity, but yet was still tractable. And what we landed on for building our digital twin of Frontier was more of a coarse grain in time. So that means we represented the system as 15-second intervals. So we basically model the system, what the system's doing at 15-second intervals. And we chose that value because that's what we collect. We collect data at 15-second intervals. So the data we collect on Frontier, on every node of Frontier, for the power, temperature on every chip on Frontier is collected at 15-second intervals. And so our initial goal was to be able to just say, can we basically replay system data at 15-second intervals and predict like the total system power. And I think the challenge is going from that to being able to reducing that time scale, because there's different time scales that are important for different things you're looking at. And so, for example, with the liquid cooling, when we submit like a HPL, a high performance LenPack run, which is what's used to benchmark these supercomputers, our system goes from 7 megawatts up to 28 megawatts in less than a second. But it takes about 5 minutes for the cooling system to catch up. So in addition to that, so in terms of the cooling system, we're on, more closer to minutes time scale. But when we get down talking about the network, we're down in about 6 orders of magnitude less. So we're dealing with things that are happening at microseconds or nanoseconds. So being able to make all those, when you have all these different models and make them work together is one of the biggest challenges. And so we started with a coarse grain feasible solution for the whole system. And then now we're trying to sort of, increase the fidelity in different areas.
Right.
Well, I think, as Wes says, that one of the interesting things about these models is that granularity. So you're always trying to move to something which is more high resolution, represents more of a real world than you can currently do now. And that needs more computing resources. But it often also, as Wes has pointed out there, has varying scales and varying resolutions inside it, which lead to these sort of traditional parallel computing problems of load balance and efficiency. And so I think there's also, with these kind of coupled and mixed environments where you have lots of different components working together, there's the challenge of what hardware you use where. It's probably not as efficient on a very heterogeneous system where you've got all the same hardware everywhere. You probably need different kinds of hardware for different parts of the simulation. And then you've got a lot of engineering work, I think, to do to connect it all up with everything else. So the data that's coming in, where does that go? Where does that live? How do you get it into your simulation? Where's your output going from? One of the things that Wes' his group are doing in Oak Ridge is a lot of visualization work. So how do you get the data out and visualize it and then get it out to the end user? And so I think there's, aside from a single simulation or single machine learning component which plugs in here, there's all this engineering matching of these things to the right hardware and trying to get them to run efficiently. So you've mentioned edge a couple of times. It could be that you're wanting to do some of the data aggregation out on edge devices where you get the overall data that then feeds through, and then you maybe want to be doing visualization and those kind of things out at edge devices, and then working out how you match your individual parts of your digital twin to the hardware you have access to. I don't think we've yet seen properly distributed digital twins where you have actual digital parts of it running in different places, because you start to run into these same problems of communication latency and connections. But that's the sort of challenges you see when you're trying to scale these things up to very high resolution, large scale.
What opens up if we do have distributed digital twins, like you just mentioned?
Well, I mean, it would open up potentially. So part of the challenge of a lot of digital twins are things like the data is sensitive. The data cannot leave a certain place. If you want to do a digital twin of the economy, you may have to have access to banking data. You may have to have access to real-time financial data. Likewise, if you want to do a digital twin of a health system or of a human patient, you may be accessing medical records and these kind of things, where actually the problem may not be the simulation or the machine learning side, but it's actually getting the data and accessing it and putting it together. And then so if you're going to end up with these disparate data sources which are quite quite restricted on where they can live, you may have to distribute out components of the digital twin to be able to do those kind of things. But it comes at a cost. It comes at efficiency or a communication cost to do things like that.
So our problem is people, as it
Problem is
so
always
often
people.
is, right? All of this talk makes me wonder what a pipeline might look like. So, Adrian, since you have some real world use case experience here, you described what all the data types are, but what does the pipeline look like? And I think that might feed into a bit more nuanced infrastructure requirements conversation now.
Yeah, so I mean, it does really vary between digital twin to between settings. But you can imagine a pipeline being starting off with the data collect, depending on where that comes from. If you think of a weather forecast, there's data coming in from satellites, there's data coming in from buoys in the ocean and from vessels and from planes that are flying. And so that's all coming together and that's continuously being collected. And somewhere that's been aggregated and worked on to get it into a form which can come into the actual core component of a digital twin. And then you will have somewhere your individual model components running. And they may be running continuously, or they may be running as batch jobs, which only start every so often and pick up the data. And, in a current scenarios, you probably don't have that data live streaming in. It's probably sitting on some storage somewhere. So your external workflow has collated that data, put it into some storage, and then your applications that make up your digital twin will start up, read that data, process it, and then produce some output. And then that output will then be processed by another set of tools to actually produce things that are useful for you. So what you might call products, data products, where you can say, okay, this is the pressure that's going to happen over the next 6 days. This is the winds. Those are the kind of things. And that's quite a different workflow maybe than to what Wes does with his data center and hardware infrastructure between. They can maybe talk a little bit more about that kind of workflow.
Yeah, definitely. Wes.
Yeah, so we start, like Adrian mentioned, we start with the data collection. And so all our data is collected into a large data lake. And then we have to, from that, when we run our digital twin, right now we don't have it where it's running sort of live alongside the actual physical twin yet, but we're working towards that. But when we run our digital twin, we first ingest the data, for example, that we want to replay, or we can take the data and reschedule it and do different kinds of studies. So we have to do that ingestion, but that ingestion involves reading generally like Parquet files and then extracting out the exact data that our digital twin needs for its simulation, which is generally like the, traces of, utilization traces of what's happening on every CPU and GPU, and a list of jobs and all those kind of things. And then our digital twin actually does it's a forward time simulation. So it steps through time, and it basically aggregates the total system power, and it makes corrections for things like AC to DC rectification and voltage conversion losses. And this actually, so the power gets aggregated, and it gets aggregated at different levels. So for the cooling model, it gets aggregated into at these different cooling distribution units, and that gets fed into our cooling model. And then the cooling model basically models the whole cooling infrastructure from, the main pumps, the heat exchangers, the cooling towers, and all that. And basically then we get power, we get the pressures throughout the whole cooling system, we get temperatures, flow rates, everything. And in the end, basically we get when our simulation ends, we get a report of all the statistics of that particular run. And so what was the throughput? How many jobs got through the system? What was the total power consumption? We even estimate like carbon emissions and all these kinds of statistics. So by doing that, then you can actually make like virtual changes or scheduling or policy changes. You can run the simulation again, and then you can see the effects of those changes.
Were supercomputers built to do all of this data management? You're talking about data lakes like you're an enterprise there.
I think that some of these concepts with data lake and some of the newer infrastructures, cloud infrastructures are starting to migrate into the supercomputing world.
How much of this workload that we've defined, this complicated variable pipeline for digital twins, can be eaten by AI over the next 5 to 7 years?
That's a hard question to answer. It's a very hard question to answer because it depends somewhat on advances in AI. And really it's those sort of explainability, reproducibility areas of AI that you need to have strong progress in to be able to replace it. So there are always parts of simulations or parts of computational approaches that are replaceable by AI. They are bounded by some knowledge where we know that what looks like correct and doesn't look like correct, or they're existing, already using stochastic processes to estimate things. So looking for using some variability and some probability in the statistics already, which is often handcrafted, but you can replace with machine learning. So for instance, I do some work with radio astronomers, build images from radio telescopes. And there, one of the important things that they have to do is denoise the image. So they get these images in, you construct the image, but you have to get rid of all the atmospheric noise and also all the noise that the image reconstruction process adds into it. And machine learning approaches, AI approaches, are very good at doing that because you can give them a defined set of, these are the original images, let's put some noise in, you take it back out, and you can make sure that they do things in a well-defined and robust way. But then there are other parts of simulations where it's much harder to make sure that the machine learning is going to give you robust results for any given input. They may give you good results for what has been trained on, but you go outside those training bounds, you're not guaranteed to get the best results. I mean, weather forecasting is a good example. So there are some excellent machine learning approaches now, which really, in some cases, do better than the traditional simulation approaches, having been trained on the data sets that the simulations produce, right? So you use the simulations, you use the ground truth that the simulations producing, and then you create an AI approach which has ingested that data, has taken that in, and can produce similar kind of results. But the same kind of approaches in weather are not as good at the moment in climate, because climate is more variable, climate is longer term, climate has things that you don't see but can often in the data sets, but can have a big impact on the outputs of the network of machine learning approach. So I think we're somewhere between those two things, somewhere between something that works really well and something that doesn't work really well. And we'll just have to see how machine learning...
That all mirrors what everyone in HPC is talking about.
Yeah.
With where does AI eat this algorithm or this approach that we've used for decades? Wes, what do you think?
Well, there are some areas that AI does really well, and then there's some areas that it doesn't. And I think one of the challenges has been when you apply AI to scientific problems is that AI basically interpolates really well. So it works really well in the data that you give it. When you start going outside, and Adrian mentioned this, once you start going outside the training bounds, it becomes really poor really fast. And that's probably, you see like hallucinations in that with LLMs, and you can imagine how this happens in the physical world. So there's been a lot of work on trying to impose physics-based constraints in the area of like physics-informed neural networks. There's been a lot of papers and a lot of work in that area. One of the criticisms is it's been hard to extend that to real world 3D problems, because imposing the constraints and imposing these kind of boundary conditions becomes difficult in the way they're done in terms of the way that physics-informed neural networks imposes them. But I would say in the near term, hybrid approaches are a really good option. So hybrid between traditional simulations and AI models to sort of utilize the best of both areas.
Right. Yeah, go ahead, Adrian.
I think there's a couple of things I'd add to that. One of them is that I think that AI can be quite good at what I would call preconditioning approaches, which is giving you a core solution which is almost correct, and then you can use simulation approaches to sort of converge it to something that's really correct. But I think the meta question here is why do you want to use AI? What's the benefit of using AI here over simulation approaches? And I guess the answer is that what you want it to be is faster. You want it to be more efficient for some definition of efficiency. So you would want to use AI to replace parts of your digital twin, which are expensive at the moment, and you want to speed them up. And I think that's a very valid thing to do if you can get past the problems that Wes has been talking about. I think the slight dangers we have are is it's good if you can speed up part of your digital twin, but there's an associated cost with training the AI. So as long as you run that digital twin a lot and the AI that you've trained for that part of a model is robust for any kinds of inputs, you don't have to retrain it often, then you get some real benefits from going to AI. The challenge at the moment is we're doing lots and lots of retraining of AI, which takes lots and lots of resources. This is why we see the large explosion in data center requirements and data center builds, because people are still training lots of models, and we need to start converging to a situation where we're not spending all our time training the models and we're actually using them instead.
True. So lightning round to close out this discussion. I feel like we've left so much unanswered and unasked, but in 5 years, I like that time horizon. It used to be 10 or 15 back in the day, but things are changing so fast. So in 5 years, what kinds of workloads, what kinds of, I'm going to start that question over again and bring it to an end. So I feel like there are so many things that we didn't touch on in this conversation. So maybe we'll have to have another one after this. But in 60, 90 seconds, I'm going to ask both of you this question. What do you think digital twins will be doing in terms of enterprise applications, scientific applications that will be highest impact by that time? Wes, I'll start with you.
Well, what we imagine and what we're working towards, but will probably take a few years to get there, is actually having a living digital twin that runs alongside the physical system and continually provides optimal inputs on how to keep the system running optimally. And so we imagine that you won't just have one physical data center, but you'll have sort of the digital twin and the physical working together in a collaborative way for optimal efficiency.
Adrian?
Yeah, and I agree, but I think I see quite strong use cases for this in manufacturing. So digital twins of infrastructure that's been manufactured, be it wind turbines or jet engines or cars, where people can really explore the parameter space for the design and the build of components and make sure that actually we get more efficient and more effective things that are built there. I'm doing some work with people who are looking at building wind turbine towers at the moment. There's a lot of work that can be done to improve the amount of materials that you use, the energy that's required, the cost that's required to build those, if you can properly model them at all the kind of scales that you need to work out when they'll break and when they won't break and how much materials you actually need to use in there. So I think we'll start to see digital twins moving into these areas and bringing some real efficiencies.
Well, great conversation, Wes and Adrian. Thank you so much for your time.
Thanks.
And thanks everybody for listening.